Hi everyone, welcome to our video. So in this video, we're going to talk about our project about the Cassava Leaf Disease classification. So in this project, we're using deep learning method, convolution neural networks to classify 5 different kinds of diseases. So we're the student from Brown University Data Science Initiative, and I am Yuchen Hua. And here's my two members, Yunshen Zhen and Su Yushen. So in this project, I will work through the outline of the method we have using and let my teammates to introduce themselves.
Hi everyone, I'm Yunshan. So I'm also a member of the Lovable Lazy team. So I'm a first year graduate student studying data science at Brown University. So for this project, I'm mainly responsible for creating the EDA, writing posts, loading TF records, and building various models to train our data sets as well as hyperparameter selections. So for this screencast, I will share all my work done in this project later in these videos.
Hi, I'm CU, and I'm also a member of Lovable Lazy team, and I'm also a first-year master student at Brown University. For this project, I help to build models and do ensemble learning, and also present some potential improvements.
So for this project, our motivation is to identify the different diseases which cause the materials harm to the food supply. And our goal is to build effective deep learning models to predict different types of cassava leaf diseases. So here's our outline. We have done the exploratory data analysis and we built the baseline model, and also we use image augmentation to improve the image quality. And the main method using here is transfer learning. And we have improved our model doing the hyperparameter training. And we also talk about some potential improvements. So next, let my teammates to introduce those details.
So I will introduce for the EDA part. So we found that there exists an imbalance in these image data sets. So from this figure, we can see that the class named the cassava mosaic disease has around like the 30,000 instance, which accounts for over like the 61.5 of the percent of the whole data set. However, the cassava bacteria blight has only around like the 1,000 instance, which only accounts for like the over 5.1%. So moreover, we also plot the image in both like the RGB color space and also HSV color space to see how like the color distributed in each images. Moreover, we also do like the image transformation on the images to see how it works. So as we know, the image augmentation is an important technique to which enables us to perform like the various transformation on images in order to expand our original data sets, save up on the overhead memories as well as make the model more robust. So in this project, we have tried like 3 different methods to do the image transformations, including using the image data generators, use the mapping functions to include the various TF.image methods, as well as using the Keras pre-processing layer API to build the Keras native input processing pipelines. So let's move on to the 3 to introduce the baseline model analysis.
For the baseline, we choose the pre-trained VGG16 model. VGG16 is a convolution neural network with 16 layers, and as we can see, the average validation accuracy for the baseline model is around 0.65, which is not enough.
For the next part, I will introduce the TF records. So from the midway post, our team decided to use like a TF rect format to do the rest of the project. So since this data set is pretty large, TF records will have a significant impact on the training time of the model. It's because that the binary data has a less space on the disk and also less time to copy. So to find out a way to load the TF records, I read this article carefully on the Kaggle to see how to build similar functions to decode like the GPH encode images to the tensors, and also read the TF-REX format, and also loading the training and the validation and the testing data sets. So after trying like I mentioned before, after trying different methods to do like the image augmentations, our team decided to go with the Keras pre-processing layer API. So we have tried like different methods, including the random flips, random crop, random rotation, as well as the random high, width, contrast, and zoom. So it's interesting to find out that if we apply like all of them to do the data augmentations, the accuracy will not be very high. So by trying the different combinations, we found that the first 3 functions are much more efficient than the other 4. So finally, our team decided to select the first 3 functions as our final data augmentations. So let's start with the inception phase 3. So inception phase 3 is a widely image recognition models. So it has 42 layers, but the computation cost is only like the 2.5 times higher than that of the Google Net, with only like 22 layers. So from these architectures, you can see that the model is composed of like several symmetric and asymmetric building blocks, such as convolutions, average pooling, and dropouts. My approach to do this one is set it as a base models and fix its weight and BIOS parameters by freezing all the layers in the inception phase 3. So then we added several layers on the top of models. So what we did was to apply the global pooling 2D immediately after the base models, where the global max poolings can be used in a model to aggressively summarize the principles of future in an image. So then we added a one flattening layers to transform data into a one-dimensional array for inputting it into one dense layers, as well as the one drop layers to overcome the overfitting issue. So finally, one softmax layer was applied to output our results. So after tuning the several hyperparameters, we decided to go with a dropout rate of the 0.5 and also batch size of the 128 and another rate about the 0.0001. So you can see the results of the training history are shown in these articles. So from that figures, you can see that the model has been able to choose like the produce a consistent validation accuracy of around like the 0.67. So also you can see that there are still some like the serious overfitting issues. So we need to deal with in the futures. And moreover, we can see that we can also notice that both the validation and the training accuracies, they exhibit like the behavior for like the each epochs. So we found that one possible reason could be that there are too many parameters in the last layers, so which could cause the parameter to oscillate between two local plateaus. So from the right figure above, we can also see that the training loss continues to decrease with the experience, and the validation loss exhibits the similar behaviors as the training loss. So both of them achieves a point of stability. So we are confident that there is also a sign of a good faith. So the second model I built here is a Resonant 15. So Resonant 15 is a convolution neural network with like the 50 layers. So from figure this one, you can see that its architecture can be split into 4 parts, and the detail of the architecture of our model is shown in this code. So for the initial stage of this model building, we first like the frozen all the layers in Resonant 15s and apply the global max pooling immediately after the base model. So in order to summarize the information of the future in these images. And we added one dense layer followed by one dropout layer to deal with overfitting. Similarly, the one softmax layer was applied to output the results. So in this case, we choose an image of the 222 and a dropout rate of 0.6 and a batch size of about the 128 and another rate is about 0.001. So you can see the result of the training history here. So from those figures, we could see that our previous model is able to produce like the consistent validation accuracy about 0.78, but also there is a serious overfitting issue after around like the 15 epochs. On the other hand, we see that the loss plot shows a sign of a good learning fit, where both like the training and the validation loss continues to decrease with experience until a point of stability. So this is one reason that our team decided to make an improvement on this pre-trained model at the final stage. So in order to improve the overall validation accuracy of the models, especially in this data set, adding more layers could have more trainable parameters to our models, so resulting a better conformance. So therefore, at this time, all layers in Resonate 15s were unfrozen, and 2 more dense layers with a different number of neurons were added to these models. So even more, we increased our image size from the 224 to 336 to capture more information in each image. So as we know, batch normalization is a popular and also effective techniques to help dealing with the overfitting issues. So in order to improve the overall model performance, several batch normalization layers were applied before like each dense layers. So in this way, batch normalization could actively center and rescale the magnitude of variables back to a given mean and also the standard deviation. So in addition, two dropout layers was added to after the corresponding dense layers. In that, we believe that dropouts could zero out some like a fraction of the models in each layer before calculating the subsequent layers. And in order to determine a dropout rate for the each layers, we apply the technique, the hyperparameter tuning techniques, which will be talked later in these videos. Last, we applied also L1, L2 regulations, which combines the L1 and L2 regulations penalties to deal with overfitting. So after finally tuning several parameters, we decided to use a batch size of 16, learning rate of about the 0.001. We can see this model have some like mild oscillation behavior in the first like the 10 epochs. However, after this point, it has been able to produce like a consistent validation accuracy about the 0.87 and achieve the highest accuracy about the 0.8834. Moreover, we can see that the overfitting issue has been successfully solved, where the validation accuracy is pretty similar to the training accuracy. And from right figure, we can see that both the training and the validation loss continues to decrease with the experience until a point of stability. So the shape of the both curves are very similar, and there is a very small gap between the training loss and the validation loss. So even more, we can see that the validation loss is slightly smaller than the training loss, which shows a good sign of the learning curves. So last, also we put our models on the Kaggle official Kaggle website, and it shows that the model has a very good performance, which achieved a score over 0.87. So we believe that this is quite a big improvement compared to our previous work.
So after trying different models like EfficientNet, VGG16, and VGG19 model, we decide to focus on building VGG16 models. I add one flattened layers, two more dense layers, followed by one dropout layer and one softmax output layer. We also choose an image size of 224 times 224, a dropout rate of 0.5, a batch size of 128, and a learning rate of 0.1 to the power of -5. Although we achieved a validation accuracy about 82%, we can see that there is an overfitting issue. Also, the loss and accuracy curve for both training and validation dataset are highly unstable. Since the overfitting problem is serious in VGG16, we mainly focus on dealing with this problem. We use L1 and L2 regularizations. In this way, the model could become less complex and become less likely to be overfitting. We also add hrnormal as our kernel initializer, which works better together with ReLU functions. Besides, the image size was increased from 224 to 336 to capture more information in each image. As we can see, the accuracy increased from 82% to 86% locally. Then we take a look at the loss and accuracy plot of our final VGG16 model. The overfitting problem of VGG16 is solved since the curves on both plots are very close to each other. The model maintains a comparable stable training and validation accuracy of 86%, and for the right figure, both training and validation loss have a sharp decreasing pattern at the very beginning and maintain a stable value under 0.7, which indicates that our model have a good performance. To enhance our model performance, we are considering combining final ResNet 50 models and VGG16 models. As we can see, compared to the best ResNet 50 models, we now have, the ensemble learning does not have a significant improvement. One possible explanation can be that VGG16 has a poor performance than the ResNet 50 models. Therefore, after adding the VGG16 model, the overall model performance will not be improved that much. Moreover, a too complex model may be inappropriate to use on the small dataset like we now have. Therefore, our group decided not to combine the VGG16 with ResNet 50 at the end. Then we are going to talk about the hyperparameter part. So an ideal combinations of hyperparameter can help us to enhance our model performance. We tune both VGG16 and ResNet15. For VGG16, we can see that the learning rate of 0.1 to the power of -5, a dropout rate of zero point 0.5, and 256 units for the first dense layers and 128 units for the second present a higher accuracy here. For the ResNet, we tune the L1 and L2 regularization parameter ranging from 0.01 to zero point 0.1. However, from the plot, there is not a big difference. So we also tune the number of neurons and 512 and 256 and 333 give us the best result. Furthermore, we also tune the dropout rate, and the dropout rate of 0.3 for the first dense layers and the dropout rate of 0.4 for the second dense layers have a higher accuracy. Some potential improvement can be test time augmentations and change random seed. We could try image augmentations on test image. Then we could use our models to predict those test image and average the prediction result. Then we are likely to get a more generalized model. Besides, since we want our model to be reproducible, we will need to think carefully when choosing the random seed in the future.
Thank you for watching our screencast, and feel free to read our blog post on the medians as well as check our code at our team GitHub repository. And please do not hesitate to contact us if you have any suggestions or concerns. We'll really appreciate your ideas.